All right. So we've got the sine of 5x, or to the fifth power x, cosine squared x dx. So we've got a multiplication. They're both trig functions. And if you remember right, what we mentioned last week, I recorded. We're good. She reminded me. So if you remember what I said last week, when we were doing things, they have a tendency to repeat themselves and kind of get screwy when we're trying to do integrate or integration by part, or integration by parts. So there's other ways to deal with this. Trig integration says that if I can rewrite everything in one term, I can use substitution. So, because remember, if I said u was cosine of x, what's du? Actually, it's negative sine of x. And if I said u is sine of x, du is cosine of x. So I can then use u substitution if I have that. So what I want to do is I want to use one of these to change it.
Well, we can cosine squared x equals 1 minus sine squared x.
Okay, so if I did that, this would be 1 minus sine squared x, right? But now I no longer have they're all in terms of sine. So I don't have something I can use to do the u substitution. So good thought, and actually we're going to do something with that, just not that one. So if you look at them, we have a 5 and a 2 here. He took the 2 and changed it to sines. Yes.
You just break out the sign?
Yes, that's exactly what I'm going to do. Yep. So I'm going to take one of those signs out. And I'm going to have sine to the fourth x, cosine squared x. All right. So now we're going to take this and we're going to change this to 1 minus cosine squared x squared. Does that make sense? Okay. So now I have all of that in terms of cosine. Correct? And I still have a sine left over to do my u substitution. So I'm going to make my u sub cosine. So it's going to be negative sine, so I'm going to put a negative sign out. That and that take care of that. And then I end up having 1 minus u squared squared. And then u squared on the outside. Put parentheses around it, u squared. Does that make sense?
1 second.
Huh?
1 second.
That's fine. All right, so now that we've got it in terms of that, we can FOIL this all out. So 1 minus u squared becomes 1 minus 2u squared plus u to the fourth. And then we have it times u squared. So I have the integral of u squared minus 2u to the fourth plus u to the sixth du.
That kind of sucks.
Are we good to that point? Bunch of algebra. Now we can do the integral. So I have negative u to the third over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus c. And the last step, I can't leave it in terms of u. I got to substitute back. And u was what? Cosine. So I have minus cosine to the third x over 3 minus 2 cosine to the fifth x over 5 plus cosine to the seventh x over 7. And yes, you could distribute a negative sign and change all the signs if you wanted to do that too. Oh, plus c, but I ran out of room. Make sense now?
Well, you sub does, yeah. Because
Actually,
it's
some
easier.
things do it for
Yeah.
organizational purposes. Why do we sometimes put the X in parentheses and not other times? Is that just like
It's
a thing that doesn't
Yeah,
actually matter?
it doesn't really matter. So it's my book publisher wants me to do it all the time, and sometimes I remember to do it on this, and sometimes I don't. But
Okay, so
it's
it
just
matters.
no, it doesn't really matter. It's just to really help you separate things out. So because there's a bunch of things next to each other, like this kind of separated it from the cosines. It's like it's separate pieces, but you don't have to. As long as you know they're separate, it's fine. You definitely would want to if it was like the sine of the fourth x plus 3, for example. Then you'd want to put that in there because it's harder to recognize that the plus 3 is part of it without the parentheses. So, but a single letter like that, you typically don't have to. So, all right. Here's the rules. Actually, I'll make this a little bigger, and then I'm going to move it. So
Whoa.
you don't have to write the whole thing. So it's in the book. It's going to be on the slide. You can always look at it later. You can always write it down later. But there's specific ways to think about it. So as we just saw in the last one, we're looking at, in essence, the odd one. That I'm going to show you. I have that rule too. So we're really looking at the odd one. Okay? As long as one of them is odd, that's the one that I'm going to break that piece off. And that's not going to be my u. That's going to end up being my du. So the other one is going to be my u. All right. So in this case, I pulled out a sign. My cosine was u. And that sign I pulled out disappeared when I did my du. So if the power of cosine is odd, I'm going to do the exact opposite. I'm going to pull out my cosine. That's going to be my u, and all the rest of them go to sine. If sine is odd, that's what we just did there. We pull out the one sign, change everything to cosines, and that one sign that's left over is going to be my u or my du. And the reason is because if I have them even, I can use my Pythagorean identity. So the question comes in is, what happens if they were both even? If they're both odd, you can do either one of them. Doesn't matter. The only problem comes in if they're both even, because then I don't have one I can split off. And in that case, I need to use the half angle formulas. So, because what that does is it gets rid of my exponent. So those are the two half angle formulas right there.
Let me write that down.
So these three identities are very useful. This one, and that one.
That's one.
Those three identities are very, very useful. It's like, because remember, basically the goal is to get rid of the exponents, or to get it into something that I don't have to deal with cosine squared or sine squared, because I can't do an integration of those. Okay. All right, so let's look at this one. So this one, the way it's set up, I don't have sine and cosine. So I can't do, I don't have an odd value there. So I can't do that method. But I can use what we just looked at. So I can change this. So remember, sine x is 1/2 1 minus cosine 2x. So I can change this to 1 minus cosine 2x squared dx. Because this is sine squared x squared. So as you can see, all this is just how can I manipulate it to come up with the number, the answer that I want, or an integral that I can do. Now I have to FOIL that out. So I have the integral of 1 minus 2 cosine 2x plus cosine squared 2x dx.
And then would we change the cosine squared to?
Yeah. So I can do the integral of that. I can do the integral of that, right? I cannot do the integral of that. So I've got to change that. So cosine squared 2x becomes 1 plus cosine 4x. Yes.
Is that an identity?
It is, no, so this rule right here, this letter can be anything. So if that was 2x, then that right there, that x has to be 2x. So that's where the 4x comes from.
Like we double our x value. We double our x value,
All right.
right?
Like, I think I got it.
So cosine, hold on, let me actually, I'm going to rewrite it because with a different letter. A is 1 plus cosine 2a. Okay? If a is 2x, this now becomes cosine 2x equals 1 plus cosine 2x. I'm replacing the a with 2x, which means this is 1 plus cosine 4x.
Also just math.
Yeah. But I will tell you, that's something that can be very confusing. It really honestly can. So, especially when they gave you the rules with x, And you're like, the x doesn't change. Well, it does. That's why you'll see sometimes they'll actually use a different letter than x.
It's like Mario collecting coins.
He's popular is what it is.
It's like, Jesus,
I
stop.
don't know if it went in a,
Silent.
That's because he's going with his phone.
Ay, ay, ay. What's up?
I forget it went in a.
Oh, you're right. I did forget the 1.5. You're right. I did forget the 1/2. I forgot the 1/2. You were right. So there's a 1/2 there. So there's a 1/2 there. And then there's a 1/2 there. Good catch.
Oh,
It was 1/2 plus.
oh. At least it's a constant, not a variable.
Yeah. And then there's the 1/2 there. All right. So now we got to clean this all up to make this a little easier for me to deal with. So this will be 1/2 plus 1/2 cosine to the 4th x. So I have 1/2 integral of 1 plus 1/2 is 3/2 minus 2 cosine 2x plus 1/2 cosine to the 4th x dx.
Why did that one in front become 3/2?
Yes,
Then
exactly.
The one there and you got the.
right. Yes. Then why doesn't the -2 cosine 2x changed?
Because that wasn't in the parentheses. And I don't have any other 2x's. I don't have any other cosine 2x's. I can't put this and this together because they're not the same.
Well,
The 1/2 on the outside of the integral wasn't distributed. It was the 1/2 on the outside of the parentheses.
yes, I know, but then why did our one change to 3/2?
Because it was
1 plus 1/2.
Okay. It's not a, it's,
Everybody else good with the 3/2 or no?
That was like the one part I really.
Okay.
I was like,
You probably understand the rest of
yeah, I do.
it. Yeah. I know.
I'm like, yeah. And I was like, wait a minute.
wait, no.
No, because I was looking at the tool like it wasn't a variable, and I was like, well, why are we not changing this?
All right. So now we have this. So now we do our integration. So 1/2. So that's 3/2x. Minus, what's the integral of cosine of x?
Negative sign.
No, positive sign. Goes the other direction. It's okay. So 2 times 1/2 sine of 2x. I'll explain where the 1/2 came from in a second. 1/2.
Was my mouth hanging over?
You weren't the only one. So I kind of figured I was going to get asked that question by most of the people there.
You gotta be messing with me.
So let's just look at the integral of 2 cosine 2x. Okay. I can't do this. I have to do u substitution. My u is 2x. My du is 2 dx.
Oh.
So 1/2 du equals dx. Now, in this situation, I had the 2 there, it would cancel itself out. Okay? In this situation, it wouldn't have. So, this right here is always going to be true. So, for example, if I look at the cosine 4th x, I would set u to be 4x. So du is 4 dx. So 1/4 du is dx. It's always going to be the fraction of whatever number is there. Always. Okay? So remember, I don't show tricks very often because if they don't always work, then you have to figure out when to do it. This always works.
It's always.
As long as it is just a number in front of a single variable. Not 4x squared, not 4x to the third, 4x, 3x, 7x, 7y, whatever it happens to be. As long as it's there, this method will always work. It is just a fraction of whatever number is there. So we call this implicit U substitution. It's like you're just going to do it and not have to go through all the steps of writing out your U substitution. Because the more complex the problem, this can get messy if you're going to have to go through and do U substitution 5 and 6 times in a problem. Okay? So you want to get comfortable with being able to just do that. That rule works. Okay?
I thought I was going insane when you put the 1/2 in there.
No, that's why.
There's no way.
Okay? So it's always the fraction of whatever number is there. And that's why there's a fourth here, because it's 1/4. Now we can clean everything up. So 3/4 x minus 1/2 sine 2x plus 1/16.
How'd you get 1/2 sine x if it's 2 times 1/2?
I'm distributing the 1/2 in the front. So yes, 2 times 1/2 is 1, times 1/2 is 1/2.
Yeah.
I don't like
I think it's easier to see the U substitution with the trig functions though.
That's true.
Because
However, I hate use of it, no matter what.
yeah, but this makes it nicer.
This makes it required. Nicer. You have to do it.
Well, my biggest problem with U substitution is being like, yes, it's a giant thing. The thing I'm doing like, is that ain't like cool.
All right. So what do you think about this one? Yeah, well, that's an irrelevant opinion,
It's
unfortunately.
undoable. Impossible. Next question.
All right. So think back to my Pythagorean identities. Way back at the beginning.
That's some good one right here.
Which one of these do you think I can use? Yeah, this one, the tangent and the secant. Okay.
I don't know.
So I have tangent squared x equals 1 plus secant squared x. So if I take this, I can split it. So if I make u tangent x, what's du? Yeah. Tangent x is secant squared x. Yes. Secant is secant tangent. If u is secant of x, du is secant x tangent x. That way. So if I split off a secant squared x, I can then change the other one to tangents. So I can rewrite this one as tangent 6x, secant squared x, secant squared x, dx. So then I can use this one here. But I also have to change this secant right here. I haven't changed it yet. I'm doing that right now. So that's going to change to tangent squared x minus 1. So I have u to the 6th times u squared minus 1 du.
What
Yes.
about-
I wrote down 1 plus tangent squared.
Oh, did I have it backwards? Did I have it backwards? I might have had it backwards. I did have it backwards. I had it backwards. I'm not having a good day today, as you can tell. There we go.
And the secant squared x just becomes du because when our u is tangent x, our du is secant squared dx.
Yes,
Okay.
got it.
Just wanted to make sure I was
Yes.
piecing that together.
Yep. So this is that.
I need to get on my neck. Oh, that's good.
Colors are nice. So I have the integral of u to the 8th plus u to the 6th du.
I have a hot pink pen.
Whatever you do, do not do your test in hot pink. I will mark it as a 0 and not even grade it.
Really?
Yes. Any kind of fluorescent ink. Like you can do your homework in it, whatever you want. Your test cannot be in
Oh, my
fluorescent ink.
test will be in pencil.
It hurts my
I
eyes.
might use like this to refer to a color on a graph, but like, that's it. This is probably- I did one test entirely in hot pink.
Yeah, I had a girl do that one day, and then I told her, I said, the next time you do it, I'm going to give you a 0. And she didn't believe me. I gave her a 0.
Which one? And this one's also purple.
No, that's it.
Close enough. It's dark purple. See that? Dark purple.
You can write it like that, or you can write it as 1/9 tangent. That's fine. Either direction is fine. Put the exponents in front, or no, because then it's a matter of, is it the x raised to the 9th power or the tangent raised to the 9th power? So if you're going to put the 9 afterwards, you have to put parentheses around the whole tangent of the x. So put the exponents just after the trig function, not the variable that's inside parentheses or whatever that's there. So this way it's clear that it's for the trig function. All right. So we've got that. So that means we can take care of it if secant is even, because I can pull out secant squared, right? And then I can replace the other ones with this. So there's a couple situations. The first one is if secant's even. That's what we just did. The other one is if tangent is odd. So if tangent is odd, we can do it because then we make remember that if u was secant, du is tangent x, secant x. So I can pull out one of my tangents if it's odd, and I can use this rule here because I only want one of them.
And the rule.
So if the tangent is odd, I'm going to pull out one of those tangents, and my u is now secant of x,
Okay.
and now my tangent's even because I pulled out one of them.
One sec. Let me just.
So, and then this one was du is tangent x, and du is secant squared x dx. That's why it works when secant is even, because I can pull out two of them and have it there.
So when secant is even. and-
So if secant is even, I'm doing U as tangent. If tangent is odd, then I'm doing U as secant.
Tangent is odd, secant, tangent is even, tangent,
No, secant is even.
secant.
Yes. There's also here, these two other rules right here. These two integrals are just ones that you're going to have to memorize or write down. They come up quite often. The integral of tangent of x is ln secant of x. And the integral of secant of x is ln secant of x plus tangent of x.
I hate the absolute value symbol. Makes so many different.
Well, because secant of x and secant of x and plus tangent of x, they can be negative.
Yeah.
Ln's can't be negative. So you need to have the absolute value sign there to use it. I believe you. You kind of need it. All right, let's look at this
Mm.
one. Actually, you know what? I want to do one before this one. I want to do this one first. Let's do this one first. All right, so I've got tangent is odd, right? So if tangent is odd, I'm going to split one of my tangents off. So this becomes tangent of x, tangent squared x.
And x is equal to
Tangent squared x is 1 minus, no, secant squared x minus 1. Minus 1. So I have the integral of tangent of x, secant squared x, minus tangent of x dx.
you distributed.
Yes.
And now.
Yes.
I'll understand it later.
I just distributed the tangent of x. All right. I now have two integrals. Because I can easily do the integral here and here. Okay, so let's look at this as two separate integrals. So that scared me. I was like,
You have it.
all right, so is tangent odd or even? Odd. I don't have to split anything out of it. It's literally just tangent. But I do have to take one of my secants out. So I have secant x, tangent x, secant x, dx. And if I make, so u is going to be secant x, right? And du is tangent x, secant x, dx. So this now becomes u du. Which is u squared over 2, which is secant squared x over 2.
But we have the other
What's that integral?
ln absolute value secant x plus
That's where those integrals for just tangent and secant come in. Because you'll have situations where you have nothing else to do except for that.
Answers aren't very.
No, they're not. They're really, truly not.
Will you ever get like a really clean one, or is it just like
The only time you're really going to get a clean one is if they're definite integrals and you can plug numbers into them. But they're not.
would we have like a definite interval of this on the test, or would you keep it to an indefinite interval? Like
Oh no, you could possibly have a definite integral. But then it's going to be like 0 to pi over 2, and you just plug those into the values.
Okay.
So the only thing that changes is that one extra step of plugging the numbers in at the end. And sometimes those don't come out to be nice. Like if the secant, if it was 0 to pi over 4, and you can't figure out the secant of pi over 4 easily, it's just going to stay ln of secant of pi over 4.
and you'd
Like,
be okay with
yeah,
that?
that'd be fine. Yeah, it's like if it's not one that you should easily know or that's easily findable, secant of pi over 4 is, but you get the point. Like they're not always going to be nice intervals. So it's cosine. It's 1 over cosine of pi over 4. So cosine of pi over 4 is square root of 2 over 2. So secant of pi over 4 is the inverse of that, or flip it over, which would be just square root of 2 actually. All right, let's look at this one. Do I have a rule for an odd secant?
No,
Okay.
we could pull one out. Make it secant.
Rules for secant? No, doesn't work that way. All right.
Then you the carrot and then you snatched it away.
Where that carrot came from.
I would split it up into secant x and secant squared x
Yeah.
and do something with that secant squared x to make it.
I have a multiplication, right?
Yeah.
Which method did we learn?
Integral by parts.
We learned integration by parts. Let's try it. So u du, v dv. So we'll set u to be secant x. That means du is secant x tangent x dx. Because I can do that. I can't do the integral or derivative of secant squared x. Well, you can. You have to do the chain rule. But I could do this easier.
Oh, because we know that.
Right. So the goal is to find things that you can easily do. Because I know the derivative of tangent x is secant squared x. So the integral of secant squared x is tangent x. So now let's see what we've got. So it's u v minus the integral of v du.
would like
Yeah.
to point out that there are 0 numbers in that, bottom little point in there.
Yeah.
That's how math, that's when math gets really fun, right?
Who said math was about numbers?
That's the number.
Huh? Exactly. Come on.
That's yours. Okay. You said that's yours.
We're writing essays here. I don't know what you're talking about. All right. Can I do that integral?
What a mess.
All right. So let's look at this.
I just want to see the plus.
All right. So tangent is secant squared x plus 1
Yes.
minus 1.
I wouldn't just believe you. I would just go with it.
I'm not on my game today. So this becomes secant to the third x minus secant x
Minus.
dx.
Oh, because then we distribute the secant.
Which I then can just split this up, make this 2 integrals. So I now have the integral of secant to the third x dx equals secant x tangent x minus the integral of secant to the third x dx plus the integral of secant to the x dx.
I'm trying to see an issue.
Good. Now, do you find this? Do you see the issue? Do you see the solution to your issue?
Which is my issue?
What did we just do?
Yeah.
We're in a loop. Good. What did I say at the beginning of this class? What happens when we deal with trig functions? We're doing integration by parts.
We end up in loops.
We end up in loops. What do we do on the integration by parts thing when we ended up in a loop?
We stop doing integration by parts.
And we did what? Yeah.
That's so fun.
What do we do?
Too.
Find where the loop starts at the beginning and then I subtract that.
Yeah. So I can move this over here. So I have 2 integral of secant to the third x dx equals secant x tangent x. What's the integral of secant x?
ln the actual value of secant x.
And I seriously got to stop writing so long because I keep running out of room plus c. How do I get rid of the 2? I just divide the whole thing by 2. So that is my final answer. Plus c. Plus c.
You know it's fun when you get Instagram recommendations of a calculus 2 professor doing integration by parts with his class.
Yes.
I don't know where secant x, tan x. Get it? Like,
This?
Yeah.
It's still here. So this part right here, I just did that part right here. I just didn't keep writing secant to the third. That came down though, once I cleaned up the.
Like next to you. I'd actually, I would have forgotten about that. I'll just write home so that I can't forget.
Or tried.
What had I written?
Oh, I don't. All right.
You keep it up here.
Yeah. Yeah, I can keep it up there for a minute. That's fine. You can keep looking. I got one more identity, one more problem to do, and then we'll just do a couple problems.
Mr. Baker,
Yes.
would you say it's an acceptable thing to say that when like you're in a loop, the solution is to just get rid of the loop?
That's typically what ends up happening. So, like when you get into the loop like that, you can pull something back out. That's how you end up getting out. That's how we did it with the E's. The E's loop too. So
what if you can't, like, is there a situation where you wouldn't be able to do that?
there's always situations that you can't do things, and then you just try a different method.
Okay, you would just say screw it.
Yeah, you just try a different method. And then there's certain things that there is no. So in derivatives, you can find the derivative of pretty much everything.
Yeah.
All right. There is situations that you cannot find the integral of something. They're just not elementary solutions. So like not elementary, like you can't physically do it out by hand.
Yeah, there's
So-
way too much.
Right. So to do those, you typically end up using a computer, and you approximate the values of them at that point. So you're not going to get an actual answer. You're going to get a numerical solution for the problem. So there is situations that happens.
That totally makes sense. You're asking building solutions.
Are we good?
No.
Okay. And that's one of those things that's where computers and stuff like that have really helped us, because we were able to do more complex things, because the computer can do the calculations out a lot faster than we could by hand. So you can get those more accurate solutions. What ends up typically happening is the computer goes back to Riemann sums. That's the way they do it. And that's how mathematicians had to do it before computers. They had to do it out literally by hand and do Riemann sums.
Is there
Yes.
a C in the derivative?
Yes, I just didn't have room to write it. There's always a plus C if it's an indefinite integral. Nope. All right. More identities.
I'm writing this down. All right.
More identities.
Will I end up with these memorized, or are they just ending up on a note card?
These will probably end up on the note card.
Okay.
I don't memorize these. Staggering identities you should know. Some of these just like half angle ones, those are pretty easy to remember. As you've seen, I have a tendency to forget the 1/2 in front, but those are typically easy to remember. These are your sum and difference integrals or
Those
identities.
are really familiar.
Yeah, they're the sum and difference identities. All right. So these come into play when you don't have, notice there's no exponents in these. So these are not ones that when you have the exponents. These are when you have numbers inside. So you have like 4x and 5x. So the goal is, again, to get it to something that, as you notice, if I go over here, I no longer have a product. So I can do the integral of each piece and then be done with it. So for this one, I have sine 4x and cosine 5x. So I have sine and cosine. So I'm using the A. So instead, I'm going to find the half. Actually, I'm going to put the 1/2 out in front. So I have sine of 4x minus 5x, which is negative x, plus sine of 4x plus 5x, which is 9x. What's the integral of sine? Negative cosine.
We
Going
just plugged-
backwards.
We just plugged that into one of our rules, right?
What? From here to here?
Yeah,
I use this rule right here.
okay, just double check, that's what I
That's fine. I use that rule right there. So sine of x becomes negative cosine of x.
About the X. Negative.
Right. So that is going to come out in front. And then I have negative cosine of negative x.
And why do we bring that up?
That's my implicit u substitution, my use thing.
Oh, yep, because the.
It's just not a fraction in
over
this case.
one,
Yeah, it's just 1/1. So this is going to become 1/9 times negative cosine of 9x plus c.
Do we need an extra end of parentheses after the negative X or no?
Probably, yeah, the way I wrote this, but yeah. Wait, no. Yes, you would have, yes, you would have a parenthesis there.
Whoa.
Into that.
Yeah, I'm just gonna,
Someone doesn't need to read this down.
no, you're fine. I was gonna put the next, I'm not done cleaning it up, so I was gonna put it here. I wasn't getting rid of it yet. All right. Now we're just gonna clean it up. So the negatives cancel each other out. So I have 1/2 cosine of negative x minus 1/9 cosine. You're right, it would be 1/18. I'm so glad I'm not doing the next section tonight.
After the negative. Oh, the fraction section.
First one.
Two negatives make a.
Positive. That's right, to describe is turn around.
Yes.
No.
And time is in odd, and you also take it out the original sign.
Probably. So
And since cosine's an even function, you just take the negative.
probably. So here's a good example of where you could have, so trig functions are the only ones where this comes up most times. You can have multiple answers for this problem that will all give you the exact same graph and the exact same value, but they look different. Okay, depending on the identities and stuff that you use. So when I grade them, if your answer doesn't match mine, I literally graph them both. As long as the graphs come out to be equal, you're good.
So just do it his way and we're all set, guys.
Well, yeah, but like he was perfect example. Cosine is even, so like I could get rid of the negative side. It'd be just cosine of x, and you'd get the exact same graph because it's symmetrical. So that's one of those things like that you can easily do where I'm looking, I'm like, okay, it's not doesn't match mine, but it's not wrong. It's right. So there's a lot of identities and rules and stuff like that in trigonometry that you can use to clean up problems and do things. And it's not wrong, but it might not look the exact same way as my answer at the end is. And that's why I just type both answers in the graph and if they match, you're good. So probably. It'll all be on my website afterwards. So you can just literally just copy it down afterwards, or just take a picture of it. Just remember to write it down, otherwise your picture is not going to help you very much. All right. Delete. Class on Thursday. Okay.
Wait, did you, by the way, on the test,
Mhm.
so we're allowed to use our phone for that?
Yeah. Let's do. Let's do this one. All right, try this one. Where do you want to start?
I don't know, once I start like yawn crying, I'm pretty much done.
What's the thing that's annoying you the most in this problem?
Uh, it's- yeah,
So let's get rid of it.
in my head, I changed it to like X.
You can't. You can't. But you have to do something first. You have to actually do the integration or the derivative. So you have to actually pull that out. So I could rewrite this as the integral of 2 cosine 3. Because I wanted to use, I was going to use m when I did the trig substitution. So you can't just get rid of it, but you can just use a quick use substitution to actually do it. Now it should look very similar to the problems that we've been doing. That's one of the nice things actually about like the methods is that if something's annoying you in the problem, there's normally a way to get rid of it.
So I already done something similar to that in my head and like still.
Yeah, I made my life easier,
Oh, it's like-
harder than.
So we want to use the which one? For sine and cosine, it was always the odd one we split off.
Yeah, I think that was a really big slide, but.
And now we set U to, let me make one more change. So U is sine of n. So du is cosine of n. dn, which we have. So that is that. So I end up getting 2, 1 minus u squared du. Yes.
So for this problem.
Yeah.
Doing it how we did the first problem is not going to get us the right result.
What do you mean?
So the first problem we did was find the integration of sine to the fifth power x to the cosine squared x.
Right.
So that's the first problem. And the way we did that problem is not how we do this problem.
Same method, except we're setting u to sine instead of u to cosine.
Yeah, but like the t over 2 is gonna.
Right. So that's why the very first thing I did before I even looked at the problem was I got rid of it.
So if you don't get rid of that, you're screwed.
No. If you don't get rid of it, you're fine, except when you do your sine of t over 2, you have to do the chain rule because now you have a function inside of a function to do your derivative of it.
So I ended up with u to the third over 3 minus u to the fifth over 5 plus c.
Right.
And my u is sine of t over 2.
Okay. So your mistake was here. So if you made u sine of t over 2,
Yeah.
your du,
Is
you have
cosine of t over. Oh, okay.
it's 1/2.
So that's
So, but that's what it's fine. You're fine.
but it's
Right.
I did it wrong. I did it.
No, you didn't do it wrong. You
Okay,
missed.
I did.
Okay, you did, but you made one little mistake. No, but you made you made one little mistake, which is easily fixable. So you would have just had to do the change rule. So when you do the derivative of sine t over 2, you get cosine of t over 2. The derivative of t over 2 is 1/2. You then have to pull the 2 out over here. So then you get the cosine of t over 2 dt. That's the only thing you miss. So and if you look here, that's where that 2 came from. I did it at the beginning, so I didn't have to worry about doing the chain rule later on. But you could have done it that way. The key is don't forget to do the chain rule when you do your derivative. Normally, when we're doing u substitution, we pick something that we don't have to do crazy things like that with, but it can come up. Other than that, actually, the rest of your problem, except for the 2 missing the 2, you were totally fine.
Wait, so even if I did chain rule, I'd still get 2 up front?
Yeah, because
You're right, maybe I do.
you have 1/2 cosine t over 2, so that 1/2 has to go over to the du. That's where the 2 comes from. Because I don't have that in my problem. I don't have that. I don't have 2 cosine n or 2 cosine t over 2. So I need to get that over to the du side. That's where that 1/2, I multiply both sides by 2.
Okay.
Normally it's like a 2 over here and I bring it over and it's a 1/2.
Okay.
But in this case, it was a fraction, so it comes a whole number.
I had it right.
So I end up getting 2. What did I make you? So all this, I'm trying to remember what you assigned. So sine 3 Yep. T over 2 over 3 minus 2 sine 5 T over 2 over 5. And I'm just going to put the C out in front. C plus that. Every time. Don't run out of the room at the end.
No. I did the same thing as you, Eugene. I didn't get rid of the 2 over 2. And I was like, maybe I can just ignore it.
Yeah, you can't just ignore it. You do have to, you either have to deal with it in the beginning or deal with it when you do your substitution. Either way will work. You just have to make sure you do that step correctly. That's why I like getting rid of it at the beginning, because then I don't have to deal with it. Yes.
Can you go to the previous
Yeah.
slide? I just want to see
Other than that,
the way you use that.
Yeah.
sorry. See, they build a company and then you do something like that,
So that's why, like, when you're looking at things, like,
right?
look at what annoys you and see if you can figure out some way to get rid of it. And looking at that problem, I knew the T over 2 was going to cause trouble, so figure out a way to get rid of it.
Would you do that to us?
Always.
We're chilling the kids. They're doing it. I know I am. I was doing it right until that last one. So that then- Yeah. perfect. Yeah. But if I didn't use stuff at the beginning, I would just be done with it.
Which one?
That one that is rare, I thought it was gonna be though. I thought the fact was really gonna like roll wrenching things. But it was just kind of there. Blow up.
I'll come back to this slide in 1 second. I'm just going to throw the next problem up and then. All right, try this one.
Put back to my rules. My trace stuff. Yeah.
No,
No.
reciprocal of it.
So the reciprocal
But that makes a huge difference.
and then yeah, opposite trace.
Like, that makes a huge difference in this problem
The reciprocal, yeah. No, because I looked at it, I was like, wait a minute.
because we haven't done anything with division. So if you do the reciprocal, you're going to have division.
So don't do that.
Don't do that.
Okay, okay. Got it.
But those are the things that when you try, it's like, wait a second, now I have division. I don't have to do division. Something's wrong here. What I didn't want you to do when you just said opposite, I didn't want you to just change it to secant, which I could see some people doing, like, oh, it's a secant. I'm good.
Well,
Yeah.
I know
It's like,
I have my tangent. I don't need that gets a secant.
Yes.
I didn't know if I had a
you
way
could do that way.
of
It might.
changing
It
that
might.
into cosine and then have some stuff cancel out.
I think that's probably going to make your life harder than easier.
So I won't do that.
Did you want us to just turn tangent something over?
That would make your life easier.
That's division though.
There's a very specific division he's doing though.
Yeah, that's correct. Yeah. Tangent with sine squared over cosine.
Mhm. Your division, you weren't going to be able to get rid of it.
It was gonna have me a fun time.
This division, you're going to be able to get rid of.
Yeah, and then we get
So I shouldn't write it on the board.
can't do it anymore. I could just make my new.
You still bring it up, right?
Yeah, you still have to do. Yeah, you're still going to have to actually. Yes. That one.
Sorry, that was on was on the board. I know it was. I got that one. But I just can't. Yeah.
That's just crazy. So as with any of these problems, you good with this? So as with any of the problems, so the more you practice, the rules are going to become easy for you to recognize. All right, you're going to recognize, okay, I have sines and cosines in the same problem. I'm probably going to have to use one of those trig rules to do it. The hardest part is the algebraic manipulation of the problem to get so you can use those rules. So like in this one, we don't have a rule for tangent and cosine. All right, we have a rule for tangent and secant. We have a rule for sine and cosine. And depending on the direction you want to go, depends on what you end up having. So Shrek over here, and I can't remember his name, but
That
I literally remember him as Shrek now because that's what I called him last week.
that's not a bad nickname though.
No. Wanted to change cosecant or cosine into secant, which you could do. But then you're going to have a secant in the bottom. And I don't have anything to do with division, and there was no way to really get rid of it. So, but we do have a rule that we can change tangent to sine over cosine, which again, yes, I have division, but in this case, I can get rid of the bottom. I can cancel the cosine out in the bottom with 2 on the top. So I got rid of my division. So then it becomes secant squared x and cosine x. And now I can use one of my other rules. So, and actually in this one, I don't even have to do any actual like switching of them. I can actually just set U to be sine of X. So du is positive cosine.
You're gonna get
You get it right one of these times. So U squared du. So it's U to the third over 3. So it ends up being sine 3x over 3. And I have enough room to write plus c this time. And I'm done. So as you can see, the hard part wasn't doing the rule that we just learned today. The hard part was taking the problem and getting it to where you could use it.
If that
Yeah.
cosine, sine, then we would not be able.
Correct. Because I would have had division left over and I couldn't have gotten rid of it. So I would have had to try something else to do it. And there might not be something else to do. That's why like when you're sitting here trying to make these problems up,
If it was sine squared, you could switch it over to cosine, throw it in the top, divide, and you'd be all right with a 1.
right, but I would still have division on the bottom. Because I would have the cosine squared on the bottom.
Cosine.
But no, he's saying if the cosine was sine.
No, but it'd be 1 plus cosine. Or it'd be like 1 minus or whatever the fuck.
Yeah, if it's 1.
So like the 1 plus it up, right?
No, you put it in the top, you still multiply,
Or
right?
the 1 plus. Pretty sure that's.
You can't distribute it.
I mean, you can.
That?
Yeah.
Turn the sine into cosine.
Wait, it is cosine.
No.
No, you're saying, you're saying turn sine 3x to turn it into the cosine.
1 minus cosine, something like that, 1 plus
So then the
cosine.
1 will fuck you up.
I would still have sine of x, and then I'd have 1 minus cosine squared x. And I still have a tangent x squared x in front of it.
Then if you put tangent in the terms of the sine.
Oh, you can't cancel that with that. Because the 1 minus. The 1's there. Yeah, you still can't get rid of that. You can't get rid of it with addition. You can't cancel through addition. You can only cancel through multiplication and division. Yes, the 1 screws it up there. And that was the thing. When you're trying to make a problem, sometimes like they just don't always work. You're going to have things that just you don't have a way to do them. So
If you had split up the sine squared to sine and cosine, and then
it wouldn't work.
sine x cosine x.
It wouldn't work.
Okay. Because I did
I'm done trying other methods.
I did that and I was like, huh.
I was like, where do I go from here?
All right, go work on stuff. We're done for the night. Yes, at home.